The third type of reaction to be on the lookout for is when you have water as a reactant. When metals and nonmetals react with water, they tend to react in some predictable ways. So when metals react with water, they tend to form bases. And when nonmetals react with water, they tend to form acids. This is a key trick here. It might be helpful to think of water as HOH instead of H2O in order to predict the correct products for these reactions. It's the same thing, right? Two H's and an O. But if you were to write water as H2O, a lot of times people write the products as being oxides. And most of the time the water, when it reacts with metals, for example, they form hydroxide products, not oxide products. So if you just take that water and write it as that HOH, then you're going to kind of automatically make the product a hydroxide. The key thing in these reactions, like all net ionic reactions, you need to know what substances you write as ions, which things are soluble, and which things are insoluble. So you have your solubility rules, but acids and bases kind of have their own special set of rules in addition to the solubility rules that you're going to learn. You might remember hearing the terms from sophomore year if an acid or base is strong or weak. When you hear strong acid or base, when you hear that term, it means they completely dissociate in water. And because they dissociate in water, they break up in water, they should be written as ions. Weak substances, when you hear that term, it means they do not dissociate in water. They don't break up. And so therefore you write them as molecules. So if you had a weak acid, I'll just make up fake acid HX. If it was weak, HX, you'd keep it together, molecule form. If you had a strong one, let's say another fake acid, HZ, we wouldn't write HZ together, but rather H plus and Z minus. There's a list of strong acids and bases. You do need to memorize this list. If you don't see them on the list there below, you can assume that they are weak. So there's a whole list there. I'm not going to read it to you, but there is a little gimmick to help you remember out of all the acids and bases that could possibly be formed, how are you going to remember which ones you're going to break up in ion form when you go to do a net ionic equation, and which ones would you keep together. So for the acids, there's this little sentence here. Claire and Brian invented nutritious candy they sold for profit. And that's to help you to remember hydrochloric, hydrobromic, hydroiodic, nitric, chloric, sulfuric, and perchloric. Your strong bases, it's all of the alkali metals. So your lithium, sodium, potassium, rubidium, all those guys, which are soluble with all anions anyway, but now we just have lithium hydroxide, sodium hydroxide, so nothing kind of special or unique there. And then the alkaline earth metals, there's just a couple of them, strontium and barium. If you combine those with your hydroxide ion, they'll be soluble. Anything else you can assume is either insoluble, just won't dissolve at all, or is so weak that it doesn't really ionize too much. So in this first example here, we have sodium being added to some water. And so again, if we think about that water as being HOH, you have the sodium combining with the hydroxide there. Kind of looks funny there. Sodium combining with the hydroxide ion, and it kind of kicks out the hydrogen ion here, turns it into hydrogen gas over there. Well, we showed sodium and hydroxide broken up. It says there, why is NaOH written in ion form here? Well, it's because sodium hydroxide is on our strong base list up here. So we would not show it as NaOH together. Instead, we show it as ions broken apart. Strong substance completely ionizes, completely dissolves in water, and so we show it broken up. If we had a strontium metal, we had strontium metal being added to water. Again, it's helpful to write water as HOH. You don't have to, but you might find that helpful. You have your strontium is going to go with the hydroxide part of that water, and then the hydrogen's going to get kicked out to form some hydrogen gas. So if we're putting strontium and hydroxide together, we have to think about, is that a weak base or is that a strong base? Well, strontium hydroxide is on my strong base list, so that means it's going to dissociate in water. It's going to break up. So when I go to write that guy over here, I would say, well, I have strontium is +2, and I would have 2 hydroxide ions to combine with my strontium +2. And then I have my hydrogen gas. That would